Before going ahead, we all should have elementary idea of EMI and current electricity. Today, this module will cover AC generator, alternating currents, representing AC, formula, graphical representation, phasor, frequency of AC and what does it depend upon, peak and RMS value of alternating current or voltage, generation of alternating voltage and current. Electricity is an important part of today's world. In the 19th century, Thomas Alva Edison invented numerous applications of electricity. One of them is invention of incandescent light bulb. Carbon was the filament, whereas alloys are applied as tungsten filament, that purpose by Hungarian inventor Imre Brody in the first part of the 20th century. Edison, however, used direct current and neglected the proposal by his assistant Nikola Tesla to make experiment with alternating current. Then Tesla joined the Westinghouse Electric Company and soon started a war between the two, the direct and the alternating current. Tesla won this battle in 1893 at the World Exhibition in Chicago. Here is the aim to explain the fundamental principle of generating alternating voltage or current. Here we can see these revolutionary scientists and their inventions like Thomson Alva Edison, who discovered incandescent light bulb, and Nikola Tesla, who discovered AC. Here we have these two waveforms shows alternating current, where electricity is mostly used in homes and throughout the world. And in another one, the direct current DC electricity flows in one direction through a wire, whereas AC electricity alternates its direction in the back and forth motion. The direction alternate between 50 and 60 hertz or 50 or 60 times per second, which depends on the country or different parts of the world. AC electricity is created by an AC electric generator which determines the frequency. AC electricity is that voltage can be radially changed for long distances transmission than DC electricity. AC can employ using capacitors, inductor in electronic circuit, which we will discuss later. In general, AC electricity is named as AC, that is wrong since that job the abbreviation for air conditioning, if we will call it only AC. So, we must call it as AC electricity. Since current defines the flow of electric charge depending on the way the flow of electric charges, the current can be categorized into alternating current or AC and direct current, that is DC. The direct current source produces DC that does not change direction with time. However, it is possible that the flow of electric charges changes direction with time periodically. It is called alternating current. Now, we can discuss here generating alternating current and AC sources. According to Faraday's law of induction, changing magnetic flux can induce an EMF. If a coil rotates in the presence of a magnetic field, the induced EMF varies sinusoidally with time and it leads to an alternating current. It provides a source of AC power. Here the symbol is used for AC voltage source. At the same time, we can see this AC waveform, how it is happening. Look at this diagram. If we see a magnetic field and in between there is a coil rotating and the wave is forming like that. That waveform is showing how the angle is changing and the wave is looking like a sine wave. Now, we will talk about how AC generator works. Look at the picture where we have a magnet and in between the magnet there is a coil. How it works? Alternating voltage may be generated by rotating a coil in the magnetic field or by rotating a magnetic field within the stationary coil. The value of the voltage generated depends on the number of turns in the coil, the strength of the field and the speed at which the coil of magnetic field rotates. now working of alternator or AC generator. As we saw the previous diagram, consider a rectangular coil having n number of turns and rotating in a uniform magnetic field, where an angular velocity of omega radian per second for the coil. The maximum flux phi m is linked with the coil when its plane coincides with x axis. In time t second, the coil rotates through an angle theta, where theta is equal to omega t. In this deflected position, the component of the flux which is perpendicular to the plane of the coil is phi is equal to phi m omega cos omega t. Hence, the flux link is at any time r n phi is equal to n phi m cos omega t. As per Faraday law of electromagnetic induction, the EMF induced in the coil is given by the rate of change of flux linkage to the coil, that is, the value of induced EMF is E is equal to minus d by dt of n phi is equal to minus n d by dt of phi m cos omega t, that is equal to minus n phi m omega minus sin omega t, which is equal to omega n phi m sin omega t, or we can write it as omega n phi m sin theta. We will call it as equation 1 or equation A. When the coil turns through 90 degree, that is when theta is equal to 90, the sin theta will be 1. Hence, the value of EMF or E has maximum or EM. Therefore, we can write equation A as EM is equal to omega n phi m, that is omega n Bm A. Since omega is equal to 2 pi f, so we can write it as 2 pi f n Bm A, where Bm is equal to maximum flux density, which is measured as Weber per meter square, and the area is measured in meter square. Frequency of rotation of the coil is measured revolution per second. If we substitute these values, then it will be E is equal to Em sin theta, which is equal to Em sin omega t, or it may be written as V is equal to V naught sin theta. Similarly, the equation of induced alternating current is, as we have seen, V is equal to V sin theta. Similarly, we have I is equal to Im sin omega t. If we look at that diagram, where we have a magnet, in between the magnet there is a coil, and we can see the direction of rotation of the coil, which is producing alternating voltage. So, now we have some common application of AC and DC electricity. If we look at these pictures, like we have some electronic gadgets, electronic devices, we have a train, motor, and so many more. These devices are the revolution or applications of AC. We can use along with the DC. And now we will discuss the difference between AC and DC electricity. As we have seen these two waveform, what actually we saw? If we saw AC, we can say in terms of energy that can be carried, for AC it can safe to transfer over longer distances and can provide more power. Next, the flow of electrons in case of AC, it rotating magnetic along the wire, and in case of DC, it magnetize along the wire. If we see the frequency in case of AC, it is in between 50 or 60 hertz, and in case of DC, it is 0. If we talk about the direction, in case of AC, it reverses, and in case of DC, it is unidirectional. If we talk about the current, the magnitude of the current varying with time for AC, and in case of DC, it remain constant. The flow of electron for AC, it is bidirectional, that is forward and backward, and in case of DC, it is steady or unidirectional, or it is only forward. If we talk about how we obtained AC, then we have AC source or generator or mains, and in case of DC we have cell or battery. If we talk about the passive parameters, so in case of AC we call as impedance, and for DC we have resistance only. Power factor for AC, it lies between 0 and 1, and in case of DC it is always 1. If we talk about waveform, for AC it is sinusoidal, triangular or square wave. In case of DC it is purely pulsating. Now we will discuss about generating direct current or DC sources. Now we will see here the waveform of alternating current. There can be various waveform for AC. The only requirement is to have alternating voltage or current. Usually AC varies according to a sinusoidal wave function. Some of the example of waveform are, yes, look at here, we have AC waveform. At the same time we can see this graphics, how 3-phase or live AC appears. If you see this, initially we have that sine wave, and now we can see the another type of sine wave in the form of AC wave, how it looks like if it is digital. Square waves are used in digital electronic circuits for testing operation. At the same time we can see these AC wave as a triangle wave, which is found in sound synthesis, and these are very useful in testing linear electronics like amplifiers. Now we will understand AC through the phasor diagram. Here this phasor diagram is showing how AC and AC voltage behaves look like this. We have this diagram, we had drawn it through GeoGebra. If you look at this, here we have one component for voltage and one component for current. Suppose I drag it like this, so the behavior of current we can see how this is behaving. You can see this is a sinusoidal wave. In the same way, if we drag this voltage component, it shows the behavior of voltage, how it changing. So we can say here current and voltage both are sinusoidal in nature. So this phasor diagram just we are trying to show or trying to prove how alternating current and voltage looks like and how it propagate in the direction of x. Here we have two more button which we can look this way. If we change the voltage, the amplitude is changing. Suppose I change the current amplitude is also changing. From these above expressions or waveform, we can talk about the alternating current and EMF. If we see the expression, an alternating current is one whose magnitude changes sinusoidal with time. Thus, alternating current is given by I is equal to I naught sin omega t plus phi, where omega is angular frequency of AC and phi is the phase constant. Instead of sine function, AC can also be represented by cosine wave, and both representation lead to the same result. Did you get how it is? We will discuss the circuit with the sine representation of AC later. Here in the above expression, I naught is the current amplitude or peak value of alternating current. If t is the time period of alternating current and f is the frequency, then angular frequency or omega is equal to 2 pi by t, or that is equal to 2 pi f, where f is frequency. The EMF or voltage whose magnitude changes with time is known as alternating EMF, which is given as V is equal to V naught sin omega t plus phi, where V naught is the peak value of alternating current. Now we can go ahead how to calculate average or mean current. When an alternating current passes through a moving coil galvanometer, it shows no deflection, that is, this is because of one complete cycle mean value of alternating current, which is 0, as AC flows in one direction during one half cycle and in opposite direction during another half cycle. But the mean value of AC is finite over half cycle. So, mean or average value of AC is defined either for positive half cycle or for negative half cycle. So, I average for the half cycle is equal to I dt, and if we integrate it from 0 to t by 2 divided by dt at the same cycle 0 to t by 2, it is equal to I naught sin omega t plus phi divided by dt at the same interval 0 to t by 2, which is equal to 2 I 0 by pi, or which is equal to almost 0.636 of peak value or I naught. From this equation we see that the average value of AC during the half cycle is 0.636 times or 63.6% of its peak value. Similarly, we can show that the average voltage or V average for the half cycle, which is equal to 2 V naught divided by pi or 0.636 V naught. During the next half cycle, the mean value of AC will be equal to the magnitude, but opposite in direction. So, always remember that the mean value of AC over one complete cycle is 0 and is defined as for over half cycle of AC. Now, we can look at how we can measure it in terms of mean or RMS value. So, first we will see this graphic. Here we can see how the AC current behaves like a simple harmonic motion wave. Here we have a two component X and Y, where we have shown the alternating current behaves like a circular wave, or we can see it in the form of simple harmonic motion. So, both way we can see. Suppose we have this X component, if we shift this X axis, we can see the behavior how sine wave is propagating. Same way we can change the frequency of the wave. Suppose I am decreasing this omega angular frequency, so you can see the wave nature. At the same time, if I change this component X component, how the wave behaves, you can look it here as it is. So, this is all about how sine wave behaves like a simple harmonic wave or a circular wave, or how it is in the form of transverse wave. Now, as we have seen that graphics where we have seen what root mean square value is, that we can explain for AC. We know that time average value of AC over one cycle is 0 and it can be proved easily. Instantaneous current I and time average of AC over half cycle could be positive for one half cycle or it may be negative for another half cycle, but the quantity I square would always remain positive. So, time average of the quantity I square is I square is equal to integral of I square dt from 0 to t for one complete cycle divided by dt from 0 to t. So, if we integrate and we solve this, we have 1 by t integral of I square sin square omega t plus phi dt from 0 to t. We will have I square divided by 2t 1 minus cos square omega t plus phi dt from 0 to t. If we solve this integral, we will have I square divided by 2t t minus sin square omega t plus phi divided by 2 omega 0 to t. If we put the limit here, we have I square divided by 2t t minus sin 4 pi plus 2 phi minus sin 2 phi divided by 2 omega. For any value of sin at 0 or pi, it will be 0. So, this whole factor will be 0. So, we have I square is equal to I naught square divided by 2. So, we have I RMS is equal to root of I square, that is equal to I naught divided by under root 2, which is equal to 0.70 of I naught. Similarly, we have V RMS V naught divided by under root 2. The same value we got. This is known as the square root of mean square current, which is called root mean square current or RMS current, or we can say it is at RMS voltage. If we see this graph, we have a wave that is showing at peak value we have I naught or V naught, we have average value for the complete cycle it will be 0, and we have that RMS value which is just lower than the average value or peak value. So, it is around 0.70 I naught. So, we can see it at the graph how it looks. Even we can see this waveform how it can be shown as RMS value or peak value. We can use this simulation or we can use one interactive for sine waveform here. So, we can see as we calculated through the graphics how this RMS value changes, how this peak value looks like, how we will measure it. So, we have some current measuring devices like multimeters. Commonly we have seen Our electrician who used to come at home, or that electronic people who used to repair the devices, they have, I think you have seen what kind of instrument they have to check the resistance, current or voltage in the circuit as per required. So, we have different type of digital multimeters, even mechanical multimeter, we can see that, and through these multimeters we use to measure the current flowing in the circuit, we measure the RMS value. Actually that RMS value is very important for the electronic circuit, even for any electronic devices it is very important, because as per that RMS value any devices is designed, and for that value we can see the tolerance of that device, whether it will work above this voltage or not, or it will crash at what value. So, for that we have to see the multimeter. Multimeter is that device which help us to measure the current at different resistances or different passive parameters, which we will discuss later. Here we can discuss now the phasor diagram representing alternating current and voltage of the same frequency as the vectors or phasors with the phase angle between them. Phasors are the arrows rotating in anti-clockwise direction, or these are the rotating vectors. Thus, a sinusoidal alternating current and voltage can be represented as anti-clockwise. Length of the vector must be equal to the peak value of alternating voltage or alternating current. Vector representing alternating current and voltage would be at horizontal position at that instant. When alternating quantity is 0, this figure below shows that the current lagging behind the EMF by 90 degree. We are using this phasor diagram to show the sine waveform. We have two component here, voltage and current, and we have drawn it along this x axis. I have taken the phase angle, and along this y axis I have both component I and V. So, suppose I change the phase angle and I shift this I value, so it looks like this. So, how this peak value is increasing as I am increasing this phase angle. At the same time, if I reverse this voltage and I increase the voltage, or at the same time I can say I am increasing this phase angle, so this voltage is shifting. So, it will looks like, if I will rotate it clockwise, so this will be like this. So, for complete cycle we can say it the behavior of AC or the current or voltage like this. So, we have almost same value if we have the same angle. So, both are at the same angle, or if I will change the phase angle between them, one is at 0 or one is at pi by 2. So, this wave will like this. So, this green one, if you see, this is for voltage and this one is for current. If we see this phasor, we have V and I and have the phase difference we have shown here of pi by 2 or 90 degree. At the same time, if you would like to see the power through resistance here, so we can just brief here. If we allow AC current, suppose I is equal to I naught sin omega t plus phi, which is passes through a resistor of resistance R, the power dissipated due to the flow of current would be P is equal to I square R. Since magnitude of current changes with time, the power dissipation in the circuit also changes. That is, the average power dissipated over one complete cycle would be P is equal to I square R, which is equal to say I RMS square R, or the rate of production of heat in this case would be P is equal to I RMS square R. Thus, RMS value of AC is that value of steady current which would dissipate the same amount of power in a given resistance in a given time as would have been dissipated by alternating current. This is why RMS value of AC is also known as virtual value of current. So, today what we have gone through, or we have learned about AC generator, alternating current, representing AC, the formula related, graphical representation of AC. We have also focused little bit about phasor, frequency of AC and what does it depend upon, peak value, RMS value of alternating current and voltage. Thank you.